Welcome to this explainer. You know, after 30 years sitting in control rooms, I've seen my fair share of plant failures. Today, we're doing a complete masterclass breakdown of a critical diagnostic manual. We're going after one of the absolute most dangerous enemies of an ultra-pure water system, that sudden, stomach-dropping decline in RO membrane salt rejection. Okay, let's dive into this. In any UPW system, the RO module is basically our frontline bouncer. It's the first line of defense. Pressurized feed water goes in, and it's physically split into crystal clear permeate and a heavily concentrated reject stream. Look, if this physical defense fails, the entire downstream system pays a massive toll. To systematically isolate and destroy this issue, we're going to follow a strict 6-part roadmap today. We'll start with RO technology basics, move into diagnosing high conductivity, explore the potential causes, conduct a root cause investigation, lay out the executing treatment steps, and wrap up with a final summary. All right, part 1, RO technology basics in UPW. Let's quickly establish the baseline of a facility so we know what normal looks like. So in a standard treatment flow, your raw water passes through multimedia and cartridge filtration before slamming into the absolute heart of the system, the reverse osmosis unit. Notice right here how the RO sits right before the mixed bed ion exchange. It's acting as a strict gatekeeper, and its sole job is to stop the vast majority of incoming ions dead in their tracks. Inside that vessel, the spiral wound membrane is just a masterpiece of engineering. Its primary job? Salt rejection. It physically blocks those ionic impurities from passing while allowing pure water molecules to literally squeeze through that ultra-thin polyamide layer. So, what exactly is salt rejection? Well, in a perfect theoretical world, absolutely zero salt should pass. In reality, tiny imperfections mean a microscopic amount always gets through. Maintaining the design rejection rate, which is usually well over 99%, is literally the lifeblood of our plant. If that percentage slips even a little, we have a major problem on our hands. Which brings us to part 2, diagnosing high conductivity. It's time to put on our detective hats and look at the crime we're trying to solve. Picture this scenario. You're sitting right there in the control room. Your pump pressures, differential pressure, and water temperature all completely normal. But out of nowhere, the water quality alarms start blaring. You gotta ask yourself, why is the permeate conductivity just creeping up day after day? The operational manual highlights a very specific set of symptoms for this. We see a decline in salt rejection, a noticeable drop in resistivity, and rising conductivity. But the crucial point is this: your operating pressure and temperature remain totally stable. When your pressure is completely fine, but your quality is tanking, it definitively proves the membrane's physical integrity or its active surface has been compromised. It's just no longer a barrier. Moving on to part 3, potential causes. Let's line up our prime suspects. According to the diagnostic guidelines, we've got 5 main culprits for a loss of salt rejection. First up, just natural membrane aging and degradation. Second, and man, this is common, oxidation damage from free chlorine. Third is a thick, nasty accumulation of mineral scale or biofoulants. Fourth, mechanical issues. Think physical punctures or broken O-rings. And finally, purely operator error, running the system at excessively high recovery rates. We can really split these into 2 camps, chemical versus physical damage. Physical damage is usually localized. Maybe a sharp carbon particle scratched a membrane or a pressure shock tore an O-ring. But chemical deterioration? That is an absolute plant-wide disaster. Free residual chlorine is particularly lethal. Just a tiny amount slipping through your pretreatment will permanently oxidize and destroy the polyamide layer across the entire array. All right, part 4, root cause investigation. Let's get into the interrogation room and isolate the actual problem. And this brilliantly illustrates why we have to be precise. When you're dealing with a massive array of pressure vessels like this, you simply cannot afford to guess. Ripping out and replacing elements blindly will cost you tens of thousands of dollars. We have to definitively isolate the exact location of the failure. The troubleshooting manual outlines a very clear veteran approach here. First, perform module profiling. We physically probe individual pressure vessels to measure the exact permeate quality. Once you find the bad vessel, always inspect the interconnector O-rings before you go blaming the membrane itself. Honestly, you'd be amazed how often high conductivity is just raw water bypassing a torn 50-cent piece of rubber. After that, make sure you normalize your operating data to see the true picture. And speaking of data, remember the number 15. The operational handbooks draw a hard line here. If your normalized permeate flow, differential pressure, or salt passage changes by 10 to 15% from the initial baseline, your membrane is definitively fouled. This is the strict threshold where just waiting around is no longer an option.
So, what do we do about it? Part 5. Executing treatment steps. Time to deliver some justice.
If the issue is fouling, we initiate a CIP, or clean in place. Now, this matrix right here is your lifeline. Dealing with calcium or metal scale, you use an acidic, low pH wash. Targeting organics or bioslime, you go alkaline with a high pH. But listen to me, here is an absolutely critical rule. If the membrane is choked with oil or biological slime, never hit it with a low pH wash first. If you do, that organic foulant will permanently congeal, and you will turn a highly expensive membrane into an unrecoverable brick. The final corrective actions are pretty decisive. Step 1, run that targeted chemical wash based on the specific foulant you've identified. Step 2, for membranes completely compromised by physical tears or chlorine oxidation, look, there's no magic chemical cure. You just have to replace them. And step 3, recalibrate your system valves and pumps to bring that recovery flow back within the original design limits. Pushing for too much product water is only going to accelerate your next failure. And that brings us to part 6, final summary. Let's talk about why rapid response matters so much. Let's move to and see how this builds downstream. The RO permeate feeds directly into the mixed bed ion exchange and EDI units. Everything in this ultra-pure water chain is tightly, intimately interlinked. If you just ignore climbing RO conductivity, that product water is going to quickly fail to meet the strict inlet standards for the mixed bed. That throws a massive ionic overload straight onto your downstream polishers. The result? The lifespan of that incredibly expensive end-stage resin is drastically reduced. Your regeneration cycles become constant, and that leads straight to severe financial losses and completely unacceptable production downtime. I want you to hear this quote straight from the diagnostic manual. It explicitly warns, heavy fouling can impair the effectiveness of the cleaning chemical. It is important to clean the membranes when they are only lightly fouled. Look, if you wait until normalized performance drops by 30 or 40%, a chemical wash is practically useless. The system just cannot be fully recovered. So I'll leave you with a crucial question to evaluate your own plant's operations today. Are you truly calculating and normalizing your daily data for proactive maintenance? Or are you just sitting back, waiting for the conductivity alarms to go off before you start fighting the fire?